In this lecture, I want to discuss the definition of the derivative at a point on a function. So let me start off with a quick sketch. Alright, so if this is our function, we'll call it f. Alright, and when I talk about derivative at a point, I mean at a specific value of the domain of the function. So we say x equals a. Alright, and what I wanted to look at is what is the derivative at this point. And graphically, what it is the slope of the tangent line. Alright, so we've seen this a number of times, this idea of the slope of a tangent line. Also, in terms of the function, it's the instantaneous rate of change. So the instantaneous part is why it's at one point. Instantaneous rate of change, which we've also denoted IROC. All right, so right at A, how is the function changing? You can think of velocity. If a car is accelerating, then what's its velocity right at one particular point? I mean, we have, nowadays we have speedometers, right, in a car that tells us that information, but if you didn't have that, then this would be one way to determine the rate of change at a single point. So I want to talk about where we get the algebraic definition from and how it's related to the graphical representation. So we've seen that one way to estimate the slope of the tangent line is by using a secant line. So what I'm going to do is I'm going to take A, this point in the domain, and I'm just going to add a certain amount to it. I'm going to call that amount h. All right, that's just kind of what I'm adding to A. So over here, I'm at A plus h. All right. Now each of these, this function is defined. Each of these are points in the domain, so we can go up to the function, find this point. So on the y-axis, this is the function value at A, and similarly, we can come up here and find the function value at A plus h. All right. So if I pull out another color here, then I could draw in a line connecting these 2 points. All right, and of course this is the secant line going through the points. What points does it go through? Well, this point right here is a f of a, right, the ordered pair, and this point right here is a plus h, f of a plus h. All right, so we could determine the slope of the secant line here, right? So the slope of any line, right? It's the difference in y over the difference in x, rise over run, however you want to think of it. But that would give us f of a plus h minus f of a over a plus h minus a. All right, so that is the slope of the secant line. And it's also the average rate of change over this interval that goes from a to a plus h. All right. So how will we use that? Well, we can allow this h to get smaller and smaller so that this point here comes in toward a. All right, and we would get, try not to turn the page too much and give you a headache, right? But as we move that in, then we would have another secant line here, and then maybe another secant line here. But eventually, as h goes to 0, we would end up with the tangent line. So remember, a tangent line just crosses or touches at a single point. One question that I've had, it's an important one. What happens, if this function were to kind of curve back down here and it crossed the function there, that's fine. We're just looking at this point of tangency right here. It only just touches in one particular spot, right at that point of tangency. And so that idea of moving a plus h, making h smaller and smaller, that's what we've been talking about for all of chapter 2. That is the limit. If we take the limit as h goes to 0, we no longer have the slope of the secant line and the average rate of change, all right? So that this is no longer relevant, okay? When we take the limit, that limit is the slope of the tangent line, okay? Now, it's important to note this is the slope of the tangent line. It's not the tangent line. It only gives us the slope, all right? Also, it's the instantaneous rate of change. And it's denoted as f prime of a. So this prime is the derivative. The way to read this is the derivative of f at a, all right? I want to show you an equivalent definition. So using a similar sketch, I'm just basically going to relabel it. You will see this in this textbook as well as almost any calculus textbook. So let me just draw in f again. So here's my f, all right? I still have this point A, all right? And we come up here to f. Here's f of a. Now, instead of adding a certain amount to a, I'm just going to come out here and take this arbitrary point and call it x, all right? So the difference between a and x is an important one here. A is a specific value of x, like 2, it's a specific x value. It could be 2, 3, 10, 1, 1/2, could be negative if it was on the other side. But this is a specific arbitrary, so in other words, it could be any specific value, but it's fixed, it doesn't move. This x is a variable. In other words, it can be anything. This is fixed. All right, so in other words, x can move, a cannot. A stays put, all right? And so what we're going to do in this case is we're going to let x approach a, all right? So you see the similarity here. Down here, we were letting h go to 0, and so that brought this a plus h toward a. In this case, we're going to let x go to a, all right? So similarly, we have this, if we come up here, here's my function value at some variable point x, right? So again, I can draw in the secant line here, all right? After doing that, again, now let's think about what these points are. This is still a f of a. That's what point that is. This point is x, f of x, an arbitrary point. Okay, now again, the slope of the secant line is f of x minus f of a over x minus a. That's just the slope formula, all right? Now, this idea here of taking x and letting it approach a is also going to be a limit, but it's going to be the limit as x goes to a, all right? So this is also another way to denote f prime of a, or the derivative of f at a, all right? Again, as you let x go to a, we would end up with a tangent line, right? This just touches at that one spot, all right? So the slope of that line is what's given right here. Okay, so that's where these kind of algebraic formulas come from, how they're related to the graph. Now I just want to go through a couple of quick examples to see how we would apply this to specific functions, because we have a lot of letters going on here, right? We got f's and a's and x's and h. So let's see how we might apply this to a specific example. So let's let our f, let's have a specific function, let's say it's x squared, all right? And we want to find out what the slope of the tangent line, or the instantaneous rate of change of this function is right at the point where x equals 2. So this is, when we give x a specific value, then this is our a in these formulas, all right? And I'm going to show you how to do this using both of these formulas, both this formula as well as this formula, just so we can see that what we end up with is indeed equivalent. So let's use this one first, all right? So if I write this out, then I'm going to have the limit as, well, let's just borrow it here, right? Let's make sure that so you can kind of see where I'm plugging things in. We're going to use this formula here. So I'm taking the limit as h goes to 0 of f of a, which is 2. So that's 2 plus h minus f of 2, because that's our a, over 2 plus h minus 2. All right, so we can simplify that. In the denominator, we're just left with h, but f is x squared. So we want to do that. We're going to take the limit as h, so that's 2 plus h squared. All right, minus f of 2, so that's just 2 squared, over, and then 2 plus h minus 2, that just leaves us with an h. So now let's go ahead and expand this out and see if we can simplify a little bit. So this is 4 plus 4h plus h squared. That's just expanding that, minus 2 squared, which is 4 over h. So continuing, 4 minus 4, that gives me 0. I'm left with 4h plus h squared over h. Notice I can factor an h out of the numerator, so I'm left with 4 plus h over h. Those h's divide out to be 1, so that leaves me 4 plus h. Now notice, if I had put in 0 for h at the beginning, right, I would have gotten f of 2 minus f of 2 over 2 minus 2. In other words, I would have had 0 over 0. So just substituting h doesn't give me, substituting 0 for h gives me an indeterminate form. So I actually have to expand this out until I end up with something that's equivalent but continuous, right? Now this is continuous when h is 0, right? Because it's defined, right? Just put in 0 for h. So now if we take this limit, whoops, I'm losing it. All right, limit as h goes to 0 of 4 plus h is 4. So what does this mean? This means, well, let's look at a quick graph. All right, so 1, 2, we know that the function value is 4, so 1, 1, 2, 4, so this would be our function. That's that half of it. It's symmetric with the y-axis, so we have it over here. And what we're saying, right, is that right here at this point, if I put in my tangent line, then the slope of that tangent line is 4. One other thing you'll need to be able to do is to determine what the equation of that tangent line is. And it's not really hard, right? We've already got the slope, okay? And what do we need in order to find the equation of a line? Well, we need the slope and we need a point on the line. But the point of tangency is a point on the line. We know that one, and we know that what that point of tangency is because it's also on the function. So we know this right here, that point is 2, 4. So there's a point. We know our slope is 4, right? So we can use point slope formula. Remember, y minus y1 equals m times x minus x1, where x1, y1 is a point actually on the line. Y and x remain variables, right? So here's a point on the line. Here's our slope. We can just plug in. We have y minus 4, that's our y value here, equals 4, because that's our slope, times x minus 2. You can simplify that if you want. You can leave it as is. Either way is fine. In the interest of time, I'm just going to leave it like it is. Okay, so I promised you I would show you both ways to do this. So let's use this formula now and just go through the calculation one more time. All right, there it is. So let's just remember what we're doing. We want to find basically f prime of 2 if f of x equals x squared, all right? So what I said before was f was this was, and we were at x equals 2. Notationally, that's the same thing as f prime of 2, right? Because this is f prime of a, and our a is 2. So we can say down here, then again using this formula right here, f prime of 2 equals the limit as x approaches 2 of f of x minus f of 2 over x minus 2. Now at this point, what I'm going to do, f of x is x squared, so I'm going to put in x squared, f of 2 is 2 squared over x minus 2. So that's x squared minus 4 over x minus 2. Now I have to notice that the numerator is a difference of squares, right? X is a perfect square, sorry, x squared is a perfect square, 4 is a perfect square. So I can rewrite that as x minus 2 times x plus 2 over x minus 2. X minus 2 divided by x minus 2 is 1. So now I'm left with the limit as x approaches 2 of x plus 2. That's it, right? That canceled out. This, remember now, again, if I just substituted 2 at the beginning, I would have f of 2 minus f of 2, which is 0, over 2 minus 2, which is 0. I would have had 0 over 0, indeterminate form. So what we need to do is plug these things in, simplify, use some of our algebraic techniques for evaluating limits, and at this point then, because this is continuous at 2, I can just put in 2. 2 plus 2 equals 4, and we can see that that gives us the same answer that we had previously.